they can do.
Oh,
They can just do this like very complex thing. I see. Yeah, that's very puzzling, right? Like seems simple, and then it evolve into something like just complex by simple rules and simple subunits.
Yeah, that's right. But by the way, I don't see any sign of Jamie Clarkson.
No, I'm here, Chris. I'm just at the controls, which is not on camera. That's good timing, because I think it brings us to the start of the seminar now. We've got a lot of people joining online, not so many in person. Perhaps it's too early to be in West Cambridge. So welcome everyone to the seminar this week. We've got Assistant Professor Yang Li, who's currently at Wuhan University working on reconfigurable structures. Before that, he was at Caltech under Sergio Pellegrino. And then before that still, he did his PhD in Zhong Yu's Oxford Group, working on energy absorbing origami. So over to you, Yang.
Okay, great. So now share my screen. Can anyone see my screen?
Yeah.
Okay, my screen is it's good, right? Okay. Yeah. Thanks for just organizing this, Jamie, and thank you, like Professor Kaladan, for joining this. Yeah, and also Charles Guy invited me. Thanks for that. And then today I'm gonna talk about the design of multi-stable morphing structures. Just let me change it into laser pointer. Okay. So today's talk is going to be divided into two parts. So first part is the work that I did with Professor Pellegrino at Caltech, and it's about a design method for multi-step structures. And it says my internet is not stable, but if there's a problem, just let me know. So this method in which we can prescribe the stable states. And also it leads to easy actuation, but the problem is its low stiffness. So in the second part of the work, which is what I'm working on right now, is that we solve that problem and then we can design such structures with high stiffness. And or additionally, we can achieve easy manufacturing. Okay, so I'll go to this one. So the whole, all of this work comes from this project called Universal Electromagnetic Surface, and it's funded by US Air Force Research Lab, and then it's based on a collaboration among all these universities. So here's the concept of the project. So you have this so-called meta surface, and on top of it, there are a lot of small antennas, let's say dipoles. So they want to control the electric current on this surface in a more or less arbitrary way, so that they can control the radiation, right? Sometimes they can make it sharp, right? Concentrated, sometimes can be scattered. And also they can repoint it, right? Do this electrical scanning, right? To point into different directions. So that's one thing, right? That's what EE people do. And then there's another aspect of reconfigurability is they want this mechanical surface to be able to reconfigure into different shapes so that they can change the field of view. And specifically the shapes, okay, just let me try to, okay, specifically the shapes they're interested in are this flat and cylindrical in one direction, cylindrical in another direction, and also spherical direction. So a natural technology people can think of is using origami, right? So this is designed and drawn by Robert Lan. So the first task when I joined this project is to analyze this structure. So this has been proposed and designed by Robert Lan. So you can see, right? This is a flat configuration. And then this two cylindrical flat configuration, two cylindrical direction configuration, sorry, and then a spherical configuration. Right? And then the first thing I did was to carry out a kinematic analysis of it. So I did it. So this is a multi-degree freedom structure, and then I just did this analysis. So and then so seems that we were advancing very good, right? In this project, seems we're already seeing the beginning of the end, right? It's working, right? We achieved the target configurations. So what else? So it turns out this is where the real problem starts. Okay, so if you're interested in how to do these simulations of multi-degree freedom mechanisms and do the pathfinding stuff, you can find it from this paper that I wrote. So the real problem, okay, is that it has a lot of degree of freedom. So how are you gonna actuate it in practice? So at that moment, I just proposed to my other colleagues, say, oh, we just mount, for instance, 12, right? Shared memory alloys, right? Those coils on top of it. And then we can just do that actuation. And people will say, oh, that's like a lot. And also, this is only a 3x3 pattern, right? Ultimately, we want to do n by n patterns, right? That will just reach a huge number of degree of freedom. So that's where the real problem comes. So at this moment, I just came up with this crazy idea. Like I was thinking, oh, is it possible that we can introduce some energy, right, into this high degree of freedom mechanism? And then we design those energy, right? Maybe we introduce some springs and design those springs so that this high degree of freedom mechanism is transformed into a multi-stable structure. So, and this specifically is stable at these 4 configurations, which are prescribed. So that sounds like a dream when I firstly proposed it, including Professor Pellegrino didn't say, didn't believe. So yeah, so amazingly, it works in the end. And this is how it works. So this is the first topic. This method of designing such multi-stable structures, which consists of rigid mechanism, right, is given. And then we attach some springs on it, and we design those springs, and then it becomes to have some local minimums at prescribed locations. So here is the design problem. So there's a mechanism being provided, and also its n target configurations being provided. Let's say for this 12-degree mechanism, I want it to be stable at the 3 configurations. So what I did first, let's introduce some torsional springs in each fold, right? Let's say there's a torsional spring at each fold, and then correspondingly, it introduces design variables. So there are rest angles, right? I can design the pre-stress. I can pre-stress it, and then I mount it on this mechanism, right? And also I can design the stiffness, right? Some springs can be stiffer, some can be softer, right? I can design for that. And the target is to make n of this stable. By stable, I mean without any external loads, right, or actuator forces, it will just stay at these configurations, right, respectively. So is that possible? It is. Let me just show you through this simple example. So here is a 4-bar linkage, and we mount 2 torsional springs at point A and point D. Okay, and these 2 springs, they have different rest angles. And for this spring at A, I kind of rotate it to 1.5 pi, and then I mount it right at point A. So it has a pre-stress, and for point D, the rest angle is at 3 pi. Okay, so now let's try to plot it in this configuration space, right? I parameterize it by theta A and the theta D, right? Respectively are the X and the Y axis. So, so there are actually 2 things, 2 parts in this plot. One is the energy in the spring. So as I specified, right, the energy, the global minimum would be at this point, right, 1.5 d pi and then 3 pi. So this is where the energy is 0, right? And then you are having this quadratic energy. When you go away from it, the energy increases. So this is the energy contour I show here. And there's a second part, because this theta A and the theta D, they are not independent variables, right? They're coupled by this 4-bar linkage. So this coupling relationship is presented by this curve. This is a kinematic path, right? So this is how these 2 parameters are coupled. So because these springs and the 4-bar linkage, they are mounted right together. They are fixed together. So the value, right, of theta A and theta D can only be on this path, right? So if you look at this plot, we're going to realize, oh, if we will try to kind of notice whether there are local minimums, we can see the 2 local minimums. Yeah, if you try to just follow this path, right, you are approaching the global minimum, right? And then once you pass this point, you are kind of getting away from this global minimum, right? So this is a local minimum, and this is another local minimum. Maybe there are more. I didn't plot it for more. So now we can see, oh, it's actually a bistable structure with 2 local minimums at these 2 points. So now I just reveal a type, right, of bistable structures, how it can be emerged. And now I want to use this knowledge to design for the bistable structures at my interested configurations, right? So that's what I do here. So now let's say if I set my target configurations at C1 and C2, which are given ahead of the other analysis, right? Then I just pointed out here C1 and C2. So how should I design my spring so that these 2 are local minimums? So you can see it very obviously, right? From a graphic point of view, I just draw a perpendicular line, right? Then another perpendicular line, and then it intersects at this O. So if I put my rest angle of my 2 springs at these 2 values respectively, then it will end up with a bistable structure which are bistable at C1 and C2. So that's the core idea of this design method. So this is just a graphic illustration, and there is a very comprehensive mathematical description of how to how to express this tangent, right? This tangent plane, right, of the kinematic manifold, because I generalize it to multi-degree freedom mechanisms, and also how to describe the curvature of the manifold, right? And then if you want to know the details, you can refer to this paper, but that's not the main topic for today. I just want to say there is this method, and I just want to show the examples instead of go through a lot of math. So here is the first example. So I started with this origami mechanism, right? And then I specify, say, oh, it has only 1 degree of freedom. And I say, oh, these 2 configurations are my design targets. And then based on these 2, I can write my equations. So the design variables are this phi 0. Phi 0 actually are the 4. I introduced 4 springs, 4 torsional springs. And the phi 0 is the rest angles of those 4 torsional springs. So I just I can write this equilibrium. Basically, if you remember that graphic view presentation, right? Basically, it's saying, oh, the tangent of that motion, basically it's motion modes, right? It's orthogonal to its self-stress at that point. At this point, motion mode, right, is orthogonal to your self-stress. So you are in equilibrium. And then also we have the second order is describing the curvature, right? And then it should be positive definite. So I have these equations. And then if you solve them, because it's a constraint optimization, or you can call it quadratic programming problem. So I need to have a cost function, right? I just want to minimize the phi 0. So I don't want to have a huge amount of pre-stress. So here is the solution. And here is the plot, right? So when you fold this structure, tracking it by θ1, the energy goes down, up, and down. And then these 2 local minimums happen exactly at where I specified. So it's an inverse design based on these 2 targets. So here is the manufacturing of such structures. And then I just get inspiration from a door hinge. So I have a coiled spring in it. And then I design this kind of a lot of holes on it. Basically, I can twist it to the specified rest angle. And then I can assemble them together. Okay, here is the demonstration that is bistable. And but the problem of this manufacturing method is very complex. And then I printed out everything, get everything. I just assembled it. It took me 5 hours, just assembled it. So it's a huge pain. So I then use the same constraints of formulation, but I use stiffness as the variables instead of the rest angles, because it's so hard to manufacture a prescribed rest angle. That's too hard. So I set rest angle for some simple values like a minus pi 0, right? It's easy. And then I solve for k. Okay, so same formulation, and then you just solve, but you treat k as the variable. So here is another example. It's a Miura-Ori again, and then you just fold it. And then you, and in this case, we end up with very simple K results. But realistically, you can also end up with non-simple, right, K results. So this is the plot shows, yeah, indeed, it's bistable at where we specified. So why is easier for manufacturing if we let K to be prescribed? Because we can use this technology called laminar emergent torsional joints. So you see, let me just play this video. So these joints, it's actually, you can see this as a torsional spring, right? But these beams, you can design them, right, to be wider, to be longer. That has a very simple analytical formula. So you can easily inversely design for a specified K. So that's why I chose K to be the design variables. Okay. So here I manufacture them. So now it takes much shorter time to manufacture and also assemble, right? So you can see the bistability. This is the first stable state, and you can just also push it, and then this is the second stable state. Well, so now we can, with this technology, right? Now we can design for prescribed stable states, right? For a mechanism, right? For a given mechanism. So now we can come back to our antenna problem or meta surface problem. So so now we work on this complex structure, which has 12 degrees of freedom, and then we use these lat joints, right? Compliant joints to for the manufacturing, and then also we introduce some unilateral constraints, try to increase the stability a little bit. To that's kind of the reason. So this can end up with 3 stable states as shown here. So these are some properties of the hinges, torsional hinges. So here is the equation. You can see now I don't have to, for 12 degrees of freedom, I don't have to use 12 actuators. I need to only use 3. You see these are the 3 actuators. So I'm loosening all these cables. So due to the manufacturing, so at its rest state, it's a little bit convex, but it should be flat. It's just because those clips being not very accurate. So I'm pulling 1 cable, you can see, and then it will snap. You see, now it snaps into a spherical configuration. By the application, you can imagine that you have your antenna tiles, right, looking at everywhere, right? You can see everything. And now I'm trying to pull another cable. Yeah, trying to pull another cable, and it will snap back to flat. Now it goes back to flat. And now I'm pulling another cable, it becomes cylindrical. See, it's cylindrical. Okay, so if I lose that, it will go back to flat. So there's nothing more. So it works, right, in theory. But here is another problem. So after I did that, I kind of just left Caltech. So they carried on with this concept to the antenna test. So this is the real test they were doing. But because I know the platform has this flaw, which is the low stability. So you can see in this final test, they have to use some external supports to hold the structure. So that's just the original merits, right, of simple actuation is just gone. So that's where the problem is. So there's a problem. Okay. So as a short conclusion for this, multi-stability we use can simplify actuation in theory, right? From 12 actuators to only 3. And then the concept behind this is based on a given rigid mechanism, and then we introduce pre-stressed springs. And then we design those springs to let the structure to have prescribed energy local minimums, right? That's the key concept. And the remaining problem is the stiffness and the stability are relatively low. And we tried to introduce unilateral constraints, and then there are following work by Charlie Dawn and he works more on this. But I think Charlie and I both agree the stiffness is still very low for such structures, and the number of designable configurations, if you introduce unilateral constraints, will be further limited. So, in a word, there's a problem. Okay, and before I left Caltech, I worked on a different approach, right, based on the same concept but different method to try to reach the same goal by using this so-called LRBT joints. I just named it in a weird way, but essentially is a 2D assembly of a lot of bistable elements. You can see that, right? So these bistable elements are designed in such a way that when you open all of them, it will just give you the design 3D shape. In this case, is a sphere, right? Just when you open all these bistable elements, it will give you that sphere. And then because it's a flat sheet, you can just bend it into sphericals. So I feel it fits the project, the purpose of the project. And the amazing feature of such structure is that it's extremely easy to manufacture. You can just using laser cut to cut this sheet, right, from single polypropylene materials. And then 10 minutes after that, you have it. Okay, so here is the actuation demonstration of such structures. So you can see initially it's flat. And then, so this is a 5 by 5. So if you are using the previous method, it has 24 degree of freedom, right? And then you need 24 actuators, but in this case, you only need 3. So the 3 actuators are, this one cable is one actuator, another cable is another second actuator, and this slider is the third actuator. So you can see now it goes into cylindrical 2, right? And then you can pull it further, you can see it opens. So that's the concept of multi-stability, right? So the structure itself guides the configuration, right? It's not that you are specifying in each joint, oh, this part goes here, this part goes there with tons of actuators, but you really program this information, right? This configuration information into the structure, into the energy. The energy knows, right? The structure, each pieces go to the right position, right? To your target configuration. So that it actually make the actuation much easier, right? You don't have to actuate a lot of parts to specify all these locations and so on. So this concept also echoes with our main idea, right? Using multi-stability to simplify actuation. Also, it reduced the actuators required from 24 to 3, right? But the sad thing is that using this method, you can only prescribe 2 stable states, right, with high stability. And also, if you look at the literature, there's another problem, is the synchronization of such assembled bistable elements is an issue, right? It's not easy. So I'm also doing some work right now on this concept, but that's also not the main part of today. So the main part is that I want to just based on the concept that I presented, and then try to improve the stiffness. So just let me give a short conclusion about this first part.
我刚争取人家都已经 conclusion 了。
So I'm trying to so what I presented is I'm using this I think the most creative idea, right? It's not a method, but the concept of using multi-stability to simplify the control of multi-degree freedom mechanisms, right? I try to make it multi-stable at the desired states. I think that's the main concept. That's the main thing. So, and then secondly, I developed the design method, right, to really realize that. And also I demonstrated the manufacturing, right? They can all be manufactured, and they are indeed easy to actuate, right? I did show that, right? With very few, right, 3 actuators, I can really maneuver it to the prescribed configurations. I did it. But the problem is it's low stiffness. And also the method is not general enough. It might have very limited designable states. So this leads to my second part of today's talk, is that we develop a new technology, a new type of structures called multi-compatible structures, and which presents very high stability, and it's based on designable multi-global minimums, right? And this work is still in progress and it's still unpublished. And okay, so let me just illustrate the idea through a simple example. So let's say, let me give you a task, okay? Just try to design a 4-bar linkage that goes through P1, P2, P3. And each point has its orientation specified. So you have these three points. These 3 points are given, right? Try to design a 4-bar linkage that goes through these 3 points. And this is not hard, right? If you go through the first year mechanism design, you're gonna learn there's a standard synthesis method of 4-bar linkage that can allow you to do that. Okay, no problem. I think every first year mechanical engineering student can do that. No problem. Okay, so here I ask you to do another thing. So try to design another 4-bar linkage, okay, goes through the same 3 points, plus the orientations being specified respectively. So that's also not hard because it's not a unique solution, right, for given 3 points. Actually, there are tons of solutions. So you can easily find another solution, another 4-bar linkage that goes through the same 3 points, no problem. Okay. That's nothing, right? So here I'm asking you to do the third thing, right? Try to combine these 2 4-bar linkages together, right? Join, by combining, I mean join the coupler links of the 2, right? The red triangle, which is very small, sorry for that, and then the blue triangle, just glue them together. When you glue them together, right? What is this structure? Is it still a mechanism? No, the degree of freedom equals to 0 now. It's a immovable structure, right? It's a immovable, but what else? So we say there's one thing else, right? Is it changes it into a multi-compatible structure. Because you think about that. So this structure is comfortable, right? It's compatible at these 3 locations, right? But in between, it is not, right? Because you can see that the red 4-bar linkage has this red path, right, which is different from the blue path. So they will create some incompatibility in between these 2 locations, right? So there's gonna be energy, right? But at these 3 locations, 2 of these linkages are both comfortable, right? So this is what we mean by a multi-compatible structure. So based on this idea, we can write a constraint optimization for our design, right? And then, so our cost function is the sum, we can write it differently, but let's say a sum of all component sizes. And then our design variables are our nodes, right? Our nodes, we have a lot of nodes on this 4-bar linkage, let's say, right? Also the nodes on the ground, right? They're all designable. The locations of them are designable. So they are A, right? A are all the nodes other than the reference points. The P are the reference points which are given, right? Also the orientation for the reference points are given. But A are these other 3 nodes, right? They are the designable parameters. So A is the design parameters. Okay, so the key part is this multi-compatibility constraints. So what are they? Let me just try to illustrate here. So this formula is saying the rotation, right, of each rod that is connected to P equals to theta, right? So this is rotation from configuration 1 to configuration I, and then you should satisfy this theta, right? That's saying just doing the rotation, these bars should not be deformed. And this is a second criteria is saying that all the bars that are in different configurations, right? If the same bars, but at different configurations, they should have the same length, right? That's what compatibility is, but multi, right? In different configurations. So this A are all designable nodes. Okay, and then also we have equality constraints, basically something like a limitation of component size, right? Each bar should not be too long or too short. So why do we do this? So what is the improvement to the previous method, right? Previously, we have this given this mechanism, right? Maybe high degree freedom mechanism, and we mount springs on it. What is the advantage of this method? This method, so there are two. So one obvious ones is they're just way more variables than the previous ones, because the whole kinematic base is designable. Everything can change. There are tons of much more variables than the previous method. And secondly, it's easier to manufacture, right? Because I really struggle with the pre-stress. And also right now, I want to manufacture something that is small, right? You want to tune the pre-stress for a small object, that's hard. So that's why we go to this method. So now, okay, let me also present some other topologies we looked into. Like this is the simple one, right? We have 2 plates, right? We have 3 bars. We can also have 4 bars. We can give a reference point, right? At this plate. We can also have 3 plates, right? We can have 3 plates, but we don't want there to be local rigidity because it might create more local kind of stable states. So we don't want those redundant stable states. So we prefer no local rigidity. Also, we can make some very complex topologies, and then we can specify one point, right? One reference point. Also, we can specify multiple reference points. That's up to you, but of course, it's gonna affect the solution. So here I show an example, and this is a topology with 2 plates and 4 bars, and this is the reference point P1, and I'm specifying 3 target configurations. So you can see I'm specifying the 3 of these points, right? At this, so I'm basically saying, oh, can this P point to be at these 3 locations with respectively the 3 orientations, and then make a tri-stable structure, right? That gives me that. That is the requirement. So here I wrote the constraint. You have this A, all these A's. You see, I already noted. So there are actually 8 of these A's, right? They are all design variables. And so the constraints looks like this, right? So this bar connected with P, when you rotate it by this theta, actually this theta is the subtraction, right, between 2 of those, and then you should end up with another like vector at another configuration. So that's saying that, and this line is describing in between all these configurations, the length of the bar should not change, right? Because this is comparing them with the configuration 1, right? This bar, when it's at configuration I, should have the same length, basically. And these are some just inequality to make the whole thing looks feasible, right? Not too distorted. And here's our cost function, basically saying the sums of all bars, right? The length of all bars should be minimum, right? We want to have something that is compact. And based on that, we can solve this system, which gives you this structure, and then we manufacture by 3D printing. It's much easier than previous ones. And also for these bars, we use TPU to provide the compliance. So here is the demonstration. As you can see, it's tri-stable. So it does achieve the prescribed stable states, and also with high stability. Actually, this stability is tunable. Think about that. Now we are using this TPU for this bar, right? Compliant bar. We can use spring steel, right? We can also use a tape spring. Think about it. If you're using a tape spring here, the local stiffness is going to be super high, right? But the energy barrier should be low, because once it's deformed, it's quite soft. So we can do a lot of things to this bar to tune the stability and energy barrier, right? Make it doesn't have to be linearly correlated. So, but here's another problem. So how to, because we manipulated by a hand, right? Hand is a very complex actuation, right? So how do we automatically know where to pull? Let's say I just want to use a cable, right? That's what we have in engineering. We pull it, right, with 1 point. How do I know where to pull? So this is another part. We want to kind of have an automatic method to find out where to pull to facilitate the desired reconfiguration. So here, I would like to introduce this method. It's called the large elastic band method. It's a method used to find the minimum energy path. So we can see, let me just try to explain here. So let's say this X and Y expands your configuration space. Okay, and this Z is your energy, right? Because your configuration changes, your energy changes, right? As an elastic structure. And then my task is that I want to find a path from configuration A to configuration B. So what is the good path? I can just go directly, right? Climb the mountain and go all the way up and then down. But that's not a reasonable, that's not a reasonable path, right? So we want to find out the good path, the reasonable path, the minimum energy path, right? In a scientific ways, minimum energy path. So this method is doing that. So here are the steps. So we have this linearly, so we start with this linearly interpolated nodes, right? Connecting configuration A and configuration B. And then we define two types of energy. One is the elastic energy, the height, right, of this node, right? The configuration has been distorted, right? And there's another type of energy, which is the distance between these adjacent nodes. Because if we have only one type of energy, when we run the minimization, all the nodes will go to local minimums or even global minimums, right? It will not form a path. We wanted to form a path. So we want to define another energy to say, oh, if these two adjacent nodes get too far away, the energy is high, right? There's another imaginary elastic band in between this kind of intermediate nodes. So when we run the minimization of these two type of energy, and then it will give us this white path, right? So you go from a minimum and in a minimum energy manner and go to from A to B. Why do we want that? Because I have a multi-stable structure. And then I know only configuration A and configuration B, right? I don't know the path in between. I have no idea. And now I want to use this method to tell me what do you think? What is the reasonable path joining these two configurations? This is the first step. And the second step is that, oh, how can I facilitate using an actuator to follow that path, right? That's the second question. So let me just show you the answer of the first question, right? For that example we presented with two plates, right, and 4 bars in between, and this is the plot of the energy. So because it's kind of a high dimensional thing, so we use this PCA to reduce the dimension, and this is the first component of the PCA. This is the second component of the PCA. These two expands the configuration space, but not in a sufficient way, but the dimension, some information is lost. And then this NEB path is like this, right? It goes from configuration A, it goes up and then down to configuration 2, from configuration 1 to 2. So looks reasonable. And then this is from configuration 2 to 3, right? Looks reasonable to me. And then here are the animation of the path. Looks also reasonable. Looks good. Okay. So, but here's the question: how do you know this is the minimum energy path? I run NEB, right, based on my understanding of it, but I want to see it. Want to see this is the minimum energy path. So what we did is we plotted in a different way. Because think about this structure, we have only 2 plates, right? And connected by 4 bars. So one of the plate is fixed to the ground, has no degree of freedom, but the other plate floating in the air has 3 degrees of freedom in 2D, right? X, Y, and then rotation, right? And I just use these 3 degree of freedom, right, parameters to track the whole system. So this X axis is the X coordinates of that reference point P, right, on the floating plate. And the Y is the Y axis of it, and the theta P is the orientation of that plate floating in the air. So I can actually, so for any point in this configuration space, there's going to be a determined energy, right? Because the bars length are defined, right? In that case, the whole system is defined. but with the with the assumption that the two plates are rigid, only the bars contribute to the energy. So now we can draw the actual energy landscape, right? So it shows like this. The structure is shown like this. No, sorry. I mean the energy landscape shows like this. So when E equals to 0.1, there's no unit here. Like it's kind of blue, which is inside. It's kind of like a channel, and then you see it's connected into a path, right? So when E increases a little bit, it forms another tube, which is outside the previous one. So when you keep increasing, it forms a lot of tubes. So this path is computed by that NEB, right? Which should be the minimum energy path. And then we look at it. Oh, indeed, it's going through this low energy area, right? Low energy channel. And then when we zoom in and we plot it with finer energy kind of grids, right? And we can see, yeah, these 2 points are global minimums, right? And they are not connected. So in between, it's a low energy path, but it's not a compatible path. So there, you see the energy does not extend all the way, right? Connecting 2 points. So it is it does confirm our understanding of it, right? It's a bicompatible structure, first of all, tri-compatible, sorry, but these are 2 compatible states. And the second, the path is indeed a low energy minimum energy path. So we confirm our method is working, our design method is working, our analysis method is working. Great. So same for this second path. So now we go to our second step of that actuator design, right? Now we have the path. Now we want to do another thing. We want to find 2 points. One point at my structure called a PC actuator, PAC, sorry, and another point at the ground, right, called a PACG, right? I just want to find these 2 points. And then when I contract these 2 points, or let's say, and then the structure, when I contract these 2 points, basically pull, right, towards each other, and then the structure can follow my minimum energy path. That was the kind of the purpose. So we parameterize these 2 points, right? They are the variables. And then we can, because we already know the path, right? By knowing the path, I mean, we know a sequence of configurations along this path. So for each configuration, I can compute the distance, right, between these 2 nodes in a, not compute, but express it in a parametric way, right? Represented by these 2 variables, right? Actually 4 variables because they are coordinates. So, and then I can just kind of give these constraints, give these requirements. I say, oh, the length should sequentially decrease, right, while you move forward. And then, of course, I have some practical constraints. Say, oh, this point on my structure should be within the plate, right? You should not go too far away. And also the point at the ground should be within a certain range. And I maximize this variation. So I don't have a very definite answer to say why this works. You can help me to answer it. I'm not sure, but that's kind of like an intuitive thing to do. And then we did it. So here is the demonstration. So we computed this plate, this point at our structure, and then computed the plate at the ground, and then we pull it. It does facilitate the desired reconfiguration. This example might be simple. You say, oh, why pull just randomly? I can do that. Well, it is true for this simple structure, but it becomes impossible for complex one. I'm going to show you in the next example. Okay, this is a simple structure, right? And then what if we design another one, right, with 3 plates, right, with a lot of bars? And then I'm demanding 2 reference points to be at 3 sets of target states, target positions. How about that? So we have 2 points, and then we assign 3 target states. So we have 6, right, 6 rows here. So for theta, also we have 2, the orientation of 2 plates, right, at 3 specified locations. So we also have 6 rows here. And the constraints and everything is the same. So now we can finish our design. It looks like this, right? The green one is one configuration, the blue one is another configuration, the red one is another one. So we manufacture them, right? It looks like this. So now I mean, for us, we handle this, right? By our hands, we're gonna know it's actually very precious to know where to pull if you want to use only one actuator. And then through the NEB and plus that actuator design algorithm, and then we can do it. So this is through the NEB, right? We find the path, minimum energy path, connecting the two. And this is the animation, right, of it. And then we feel, well, looks reasonable. And then we can compute the locations to mount our cable. And here, we're gonna show it works. So this is simulation. This is the real model. And then I'm gonna just pull this cable, you see, here. And then, okay, it's gonna achieve the desired reconfiguration. You see, it's just the same. I can play it again. Same as the simulation. You see, this is so the whole, all of these steps forms a kind of design procedure, right? Step by step. Okay, so far I only presented basically 2D problems, right? We have a lot of 3D manifestations of the same design principle. So here, I don't want to go into details, but here is a 3D structure. We basically join them by universal joins, and all these bars are hydrohedrons because they all go to 3D. The bodies are polyhedrons. So here we show the reconfiguration, and then also the plot. Because I look at the time, I feel I need to rush. It's already 10 to 8. Sorry, from my time. So you can see from the 3 configurations, they can just go by this. Just energy, they need to overcome the energy barrier and go to the other side, right? So this says the same principle works in 3D, and but if you look closely for this animation, the self-contact problem is not resolved in this case. And also, we are interested into other types of spatial structures. So, but what are they, right? When people talk about spatial structures, what are they? So now we'll go to them. So first type is 4R linkages. Right? So a little bit of history, I'm sure that you guys are very familiar with. So Geoffrey Thomas Bennett developed this Bennett linkage, right, from Cambridge. So it's amazing because normally we think about spatial linkages. It has to be 7R, right, to be able to have 1 degree of freedom. 4R is, it has no degree of freedom, right? But he developed this relationship, say, oh, if these are satisfied, then it forms a over-constraint mechanism. It's still movable. So here are some examples. Bennett linkage, this is the motion of it, and a Bricard linkage, right, with 6R. This is the motion of it. So here I want to give a statement. So for here, okay, so that's the principle that is guiding our following research. So I believe this. For all over-constraint mechanisms, you can actually design them into a multi-compatible structures and with more design space. Think about that, right? So over-constraint mechanisms has a higher requirement, right? Along this path, it has to be compatible all the way. But multi-compatible structures, it doesn't have to be that serious, that rigorous, right? That strict. It needs to only be compatible at several discrete states, and that's enough. And then that's why I say it has more design space, because the constraint is loosened, right? It's less. So here I'm gonna, because of the time, I'm not gonna go to just a lot of details. I'm just gonna keep going, but it's the same step. Okay, same step. And then here we develop a bistable 4R. You can see this is the simulation. This is the energy plot, right? It goes up and down. And here is our prototype. So it's also specified. It's specifying this hinge to be at 0 and 180 to be stable. So you see, it's also bistable. And also we can do more along this concept. We can develop into a 6R. We are working on that, and also more stable states, not just bistable, but tri-stable. And also we want to coupling all this 4R and 6R into multi-loop structure. And then here are some illustrations. Okay, that's one. And another one is we also want to introduce this into thick origami. So as you might know, origami is essentially a spherical linkage, right? And it has zero stiffness. There are people who transform it into thick origami, has 1 degree of freedom, but essentially is another type of over-constraint mechanisms. So as I stated, I said I believe all the over-constraint mechanisms can be transformed into multi-compatible structures, right? And with more design space. So I'm not going to talk into details, but I'm because I just want to like rush finish it in time. So this is a bistable origami. You can see it's a 4R, and then we design the thickness. You can see it's stable. But in this case, we met with some problems. If we want to introduce more variables, because previously when people design thick origami, they only use variation of thickness as the variables, and we want to kind of enlarge our design space. So we introduce offset and twist angle. So by offset, so the original origami, we want to increase the design variables by introducing this D, right? It's offset. We kind of shift its hinges, right, freely. So the previous constraints, we previously only have H as the thickness, right, as our design variables. Now we double it, right, by introducing D. So now we can design for more complex stabilities. You can see this one, it can be stable at a prescribed intermediate state. It doesn't have to be flat or fully folded. So it can reach to more different designs. This is tri-stable 6R, and this is a 4R, but with more vertices. Okay, I want to kind of replay this a bit. Oops, I think okay, okay, that's fine. So additionally, we also introduced twist angles. So you see this beta is newly introduced to further increase the number of variables here. So why do we do that? Because we did a parametric study, and the x-axis is the difference between the two specified stable states. If they are very close to each other, you're going to end up with something that has very low stiffness. But if they are like separated apart by a lot, then you're going to have large stiffnesses for in between. And if we introduce this additional twist angle, you can see the stiffness is overall higher. Right, here's another video, and we can see it's I think it's a 6R bistable, and this is showing it's stable in the intermediate states. Okay, and then it goes back. Okay, that's pretty much all the videos. I'll just give a short conclusion. So basically, what we are trying to do is to make the reconfigurable structures be more useful, and then we can do this inversely designable reconfigurability by forming the design problem as an optimization problem. And also we achieve easy manufacturing. As you see, we use a lot of compliant mechanisms, and also we achieve the removal of pre-stress. That's a great advancement for manufacturing, right? And also the key concept of all I've been doing is to achieve easy actuation through the combination of multi-stability and also pathfinding, right? NEB, so-called, and also this actuation location design, right? That's the that drives the key logic of this research. And also we showed that we achieved high stability, high stiffness, and also tunable, right? And through this multi-stability to achieve these multi-global minimums. So for the next, that we want to extend this multi-compatibility concept to other structures like kirigami, origami, and also we want to embrace this applications in other disciplines, like this meta-statistics, but reconfigurable, right? Using multi-compatibility structures, and also this mini micro magnetic robots, because I realized in this mini or micro magnetic robots, it has the same problem of the lack of actuation, because you cannot do the same thing as Boston Dynamics, right? You actuate a high degree of freedom mechanism with a lot of actuators, tell each part to do exactly this. In this micro scale, right, the actuation is very vague, it's very abstract, right? You just apply the field, like apply the gradient of the field. That's pretty much all, right? But with this multi-compatibility programmed, right, inside of the structure itself, remembered a lot of complicated configurations, right? Then you just need to use a simple actuation, right? Same problem, easy actuation, simple actuation, then you can just deform into the desired ones, right? Can program a lot of shapes into them, can do something more complex. And then the last one I'm looking at is to use these structures to do to design robots with impulsive motion. As you can see, this snap through, right? We can kind of engineer a prescribed snap through, things like that. So at last, I would like to give acknowledgement to my previous supervisor, Professor Pellegrino, and my previous colleagues at Caltech. And also I want to thank my current students who actually did all this work. So they're amazing. Thank them like very much. And then that's all. Thank you. Thank you. Yeah.
Thank you very much, Yang. That was an excellent talk. Are there any questions from anyone online or in the room? Well, there's not any in the room. Any questions? Just raise your hand if you've got a question. No, looks like there's no questions. Chris. Yep.
Also, Professor, yeah, Professor Culloden.
Yes, I was just going to say that the most polymorphic system I've dealt with is bacterial flagella, which can adopt a range of 12 different states, each with a different, they're all corkscrew shapes, but they have different pitch and
configurations
and angle. Yeah, I mean, you can describe a spiral by means of 2 degrees of freedom, and there's a whole range in this particular case of bacterial flagella, and they operate really by having they're built of subunits, which are proteins. And the key trick in those is that you have 2 proteins which can bond together in 2 slightly different conformations. So you have a bistable conformation, which might involve a slightly different angle, twist angle, or a displacement. And so nature has devised a way of designing structures which have this key feature of the subunits are basically 3-dimensional lumps which have various bonding sites. And so you can, nature has devised a way of producing these different helical waveforms. So the key feature there, as I said, is subunits which can connect in 2 slightly different ways. So it's a sort of constrained geometry arrangement. So it's sort of compatible conformations, I would say. Sorry, that's a bit
Yeah.
confused, but
No. I feel it's very inspiring. I mean, I will email you and then you can send me more. But here is my understanding, because I talked about this manifest. Okay, so first of all, you said that in these bacteria, right, like there are proteins, and then you only change a little bit, and then it will end up with something that is very different, right? Only change the twist angle a little bit. So that's, to me, kind of like multi-stable structures, right? And then you have the same, it's consistent with same materials, right? Same subunits, but with one of them maybe slightly like a twisted, and then it ends up with something different. So how this is related to what I'm doing right now is that we actually struggle with what kind of 3D topologies we should look at to make it multi-stable. So you see, we looked at into thick origami, right? We look at into band linkages. And that's because we look at everywhere, right? We want to see, what things we can make them multi-stable, okay, multi-compatible. So now you give us another inspiration, say, look at these biological structures. They are also the potential candidates for your design. So I really appreciate this insight. So may I ask you for probably, I'm gonna email you and then you can just share a little bit of literature with me, and then we can look at into those interesting structures you are mentioning. Because some things you mentioned, I don't even know what it is. Some words I don't even I don't even understand. But I can see there's something intriguing going on. And then thanks for this comment.
Yes, actually, a relatively simple problem is the hemoglobin molecule, which consists of 4 almost identical components which connect together in a particular way. But when the purpose of this molecule is to transport oxygen around in the blood, and when the oxygen is incorporated to make it oxyhemoglobin, these 4 components which fit together in a sort of tetrahedral way undergo a change in which comes about because the way in which these 4 components are connected involves a small change in the position of the binding together of these biological structures called alpha helices. So it's because of the possibility of alpha helices binding in different conformations that the hemoglobin molecule works. So that is a good starting point, I think.
Yeah. So the binding of oxygen just changes, as you said, a little, right? Like a little things.
It has to create space for the oxygen. It's the heme group that has to be altered when the oxygen comes aboard.
Okay. Well, thanks. I'll look into this molecule and then see how oxygen changes its kind of small things and then end up with a different configuration. And then we can get inspirations to see, maybe that's the 3D structure, 3D topology we should look at, and then to employ our this design method and then create some more spatial, right? Yes, great. Yeah, that's a great suggestion. Thank you. Yeah.
Do you have a question?
Yes, thanks, Jamie. Thank you, Professor Yang Li, for the talk. It was very inspirational. I have 2 questions. One question is about the NEB computational time when you're designing these structures. So I'm wondering how long does it take to design like a 4-bar, and when it comes to spatial, when you have so many variables, how long does it take to run one simulation to come up with the 3 stable states? That's my question. Yeah.
So, well, thanks. So like this one, okay.
Yeah.
I think for, okay, actually my students did this. I mean, but I also wrote the code and I ran a lot. I think it does take a long time to converge, because you have 2 parts of energy, right? And then it will reduce, right, step by step, each, because you are moving all the nodes, right, simultaneously, right, try to reduce the energy. So you see if the structure, okay, because you see if I do simulation, right, so each node and my computer has to only deal with 1 node at a time, right? So these are the, so I mean, I'm talking about 1 configuration point at a time, right? Because let's say this structure, it has, let's say 10 points, right? I have to, so my variables, right, only have like 10 points in it, right? And then I'm iterating, like doing the simulation, I'm updating these 10 points. So this structure is deforming. But when you do this path optimization, it's different. So for each configuration, let's say along this path, I have 50 nodes, right? 50, right? 50 nodes. Then each iteration, I'm updating all of them at once. So for my current variables is my 10, right? 10 configuration points, right? At 1 static state times 50, right? So my computation variables is huge. You can see that. And I'm updating all these 50 configuration points each time. And using laptop, let's say, for this, I don't know how long. Like, can Eileen, can you help? Like, just tell me, like, how long did you use to run this, to converge into this path? Are you there?
Okay. Here. For the 2D examples, maybe the time maybe 20 minutes or 30 minutes, and it can converge to a very ideal values. And maybe for the 3D examples, and the variables are much, and then the time may be 2 hours or 3 hours.
So for 3D, like you're talking about this one, right?
Yes.
Okay, if you found a path in this one, 2-3 hours, by using your laptop, you're talking about. Okay.
Yeah. Yes.
Okay, thanks. Does that answer your question, Charles?
Yes. Yeah. That's very. Thank you for that. And my second question is, when you're doing these transformation, obviously there might be some self-intersecting between bars. Because that's like how things might move, and the stable states, it's maybe it's impossible to move, for example, from like if we have a more configuration, there's like self-intersecting to move in between. How do you eliminate that simulation?
Yeah, very good question. So in simulation, we don't eliminate, we ignore contact, they just penetrate. Okay, but in design, right, you see all our physical models, they don't have intersections, right? They can go there because we thought about that beforehand. So how? So there are 2 types. One is 2D, right? When you have 2D, you just divide them into different layers. Based on this minimum energy path, we know how each component is moving, right? And then we can just draw some kind of very illustrative sketches to layer them into different layers and connect them. Because it's only one path, not everywhere, not everyone is moving. It's just on that single path. No one is touching each other. If you are touching, we divide them into different layers. That's no problem. And this is exactly what this slide is about. For 3D problem, I mean, we haven't accomplished it. And then there is self-contact problem. So that's why we kind of learn from other 3D structures like 4R linkage, right? Because it doesn't do intersection, right? We borrow these successful examples, and then based on them, we do our multi-compatible design, because they by themselves, they don't. And also after the design, because we already modified a little bit, right? We're gonna just examine them in SolidWorks, right? And then because if you can actually slide your structure along the hinge, right? Because it doesn't change the real thing. So you can just slide and to see with your eyes manually to avoid that. That's how where we are right now.
Thank you. Yeah, thank you very much.
Yeah, thank you, Charles.
Okay,
Yeah.
any further questions from anyone? Yeah, I think we've got yeah, go ahead.
Hi, Yang. Thanks for the talk. So, based on my understanding, so you use spring hinges at the beginning, and then you
Yes.
use deformation bars made by TPU for your planar 4R linkages. And then later, for over-constraint linkages and thick panel origami and terigami, are you using the deformation of panels, or are you using the deformation of hinges for the end?
Actually, we did both, but in this case, you see, for the thick or for this one, right? It's actually by the hinges. You can see the hinge are made out of TPU, right? The
So for
bars
this-
are from PLA.
Okay.
So this is by hinges, but it doesn't matter actually. Anywhere that's provide the compliance is okay. So for the thick origami, it's done by the whole thing, but mainly hinges. Mainly hinges. The whole thing is out of TPU.
I see.
Yeah, does that answer your question? Yes. Because the static states are multi-compatible, right? In between, it will create energy one way or by another, right? So it just anywhere where it's weak, it will deform at that location, right? So it can happen at well, wherever. I mean, I don't care, to be honest.
Okay. Another one is, can you go to page number 16?
Okay.
16.
Oh, 16. Okay, sorry, I thought 60. Okay, just let me just go here. 16. Okay, this one.
So this one is very interesting to me. You said there are two kind of connections. One is using lat joint, and the other one is using unilateral constraints to achieve this 3 stable state. And I observed there are.
So I see actually this. So you see, the lat joints is the torsional spring, but I'm introducing a clips on top of it to hold it at my desired state while keep its pre-stress, because this can increase the stability. Otherwise, the whole thing is too floppy.
I see. So if you go back to page number 16.
Okay, sure.
The two stainless steel strips from one panel, and there's another stainless steel strip from the other panel. Actually, this is what you call unilateral constraint. And the black bit is your lat joint.
Yes, exactly. Right.
Okay.
Is that, yeah.
Yeah.
Okay.
Thank you.
Yeah, that's
also, what is the rotational limit of your lat hinge that you have tested?
You mean elastic limit?
Elastic limit.
Basically 180 should be fine. Look at this one. Just 180 is fine. Well, of course, it depends on your beams, right? But the 180 should be still elastic.
Did you observe any out of plane torsion in the bending?
Yeah, exactly. You see, I have these tapes at 2 sides, right?
Okay.
Yeah, tape them. Yeah, to avoid that. Yeah, it has, of course.
Okay. Thank you.
Yeah, thank you, Jane.
Yeah, I think that's probably all we have time for. Thanks Yang for an excellent talk. For joining us next week, we are back in the seminar room at 3 p.m. and we have Dr. Brian Shield talking about soil structure interaction. And of course, anyone who has the link is always welcome to join on Zoom. So thanks again, Yang. And it's been recorded and I'll be sending you over the recording.
Yeah, great. Thank you, Jamie. Thank you, everyone. Thank you for your